Good morning, everyone. Welcome to this webinar entitled How to Troubleshoot Induction Motors using the Megger Baker 105. We'll have a look at the test capabilities of the MTR and how to apply them when testing motors and other rotating machines. Let me just share my presentation. Okay, so by way of introduction, my name is Mike Herring and I'm the Regional Manager for Megger Baker Motor Testing Products. And I'm covering the north part of Europe, Russia and CIS countries, the Middle East and Southern Africa. I've worked with Baker products for more than 30 years, mainly as a distributor, and then since 2011 directly for the factory. So my role is to support the local Megger teams in my regions, their distributors, and of course, most importantly, our customers. This includes technical support, data analysis, demonstrations, delivering training courses, and so on. I've also delivered paid-for training to industry, including marine, paper, and power generation. So I have a practical experience of using motor test equipment in real-world situations. So what is the MTR105 and what can it offer you? In simple terms, it's a multifunctional handheld test unit that replaces several single-function units. By incorporating a suite of IR tests, a voltmeter, a motor rotation test, continuity tests, a digital low ohms resistance test, or DLRO, an LCR meter, and also a temperature sensor into one small handheld unit, we offer the customer numerous benefits. And we can even export that data that we take from the MTR into our PowerDB Lite software, which is a free of charge software to allow you to create professional reports. So some of the benefits include the small form factor. It's light and very easy to carry. We have the possibility to use rechargeable batteries or just AA's otherwise. We have intuitive controls and graphics, so it's very easy to use and to learn how to use. The unit provides insulation resistance values which are temperature corrected, which is very important and we'll talk about later. It can even operate up to 3,000 meters above sea level if that's important to you. We've already said it's light and portable, and we have the ability to store up to 256 records or motors. All of the tests go into that record, and then it can be transferred to the software that I mentioned earlier. Another benefit is you have one single instrument to calibrate each year instead of 6 or 7 units. So you have a cost saving and also a time saving. We have one single instrument to carry to site or around the workshop instead of multiple units. So did we forget one of the units when we went to site? Do we have the right leads with it? The MTR includes everything in its little carry case, so nothing is forgotten. And we have one single instrument to connect and test with, so we save time when we're testing, and we are much more professional. So the MTR105 standard features include an insulation resistance test, which includes the guard feature, for those that you know guard. We have a 2-wire continuity test, a Kelvin low resistance test down to 1 milliohm, that's a 4-wire measurement. We have a temperature measurement via a Cat2 600 volt type T thermocouple, which is included. And this allows for the temperature correction of the IR test that we spoke about. We have a voltage measurement function, both AC and DC up to 1000 volts, and also true RMS measurement for inverter drives. We have a power supply phase rotation test as part of that voltmeter. And we also have a motor direction of rotation test. Again, we'll come back to that later. We have a diode test. We have an LCR meter giving us inductance and capacitance tests. And again, we have the data storage and transfer via USB. So ease of use is key with the MTR105. All of the tests are selected by the rotary switch. And then within each test, access to the submenus is controlled by soft keys. And these include the main test button that we see down here. We have a save button. We have a screen brightness button. We have a buzzer selection, so we can set a buzzer to sound at certain times. And we have this dual lock feature, which allows us to lock the test if we're doing an installation resistance test, for example, so leave the tester running at that specific voltage. And we can also use this button before we start a test to verify the connections. And when we press it, we will get this image here on the right, which shows us where to connect our test leads to, depending on the test that we're running. And then each test, as you may have noticed, is color-coded. And this is color-coded to match the other Megger test equipment that you may be familiar with. So IR is always red, winding resistance, low ohms winding resistance is always yellow, etc. So let's look at the test one by one, starting with insulation resistance. The IR tests have preset voltage levels of 50, 250, 500 and 1 kV. And there's also the ability to set any voltage between 10 and 1 kV in 10 volt increments. And that's done through the settings screen. Then within the IR test screen, we have the options of IR or spot check. We have a 3-phase mode, which allows us to make an automatic phase-to-phase IR test. So U to V for 1 minute, V to W for 1 minute, and W to U for 1 minute, fully automatically. And of course, to do this, we must be able to open the neutral point of the motor. Otherwise, we'll have a short circuit between the phases. We have a PI test, which is our 10-minute megohm test. That will provide us with the PI ratio after 10 minutes, which is calculated by dividing the 10-minute IR value by the 1-minute IR value. We have a timed IR test, which is typically 1 minute, but you can change that time within settings. And then finally, we have a DA test, or dielectric absorption test, which is the shorter version of the PI test, where the ratio is taken between 15 seconds, 1 minute, or 30 seconds and 1 minute. So these tests are critical in evaluating a motor's winding for buildup of dirt or moisture, contamination, deterioration of the insulation, and whether or not the winding is able to take a high voltage or high potential test, and therefore is it suitable for further operation. The data can be trended over time to show the speed of insulation deterioration. But again, to have a meaningful trend, we need to temperature correct the IR values. Again, we'll look at that in due course. We have a 2-wire continuity test that has a range from 10 milliohms up to 999 kiloohms and can be set to bidirectional or single direction. And we have 20 or 200 milliamp test current. We also have the 4-wire Kelvin resistance test, or the DLRO test, and that has an automatic resistance range from 1 milliohm up to 10 ohms with a resolution of 0.01 milliohms. And we have 200 milliamp test current for this test. So where highly accurate low resistance readings of windings and connections are required, the DLRO function must be used. So for example, if we have a winding which is around 10 milliohms, in theory the continuity test can measure that. But if one winding was 9.5 and one was 10.3 and the other was 10.8, that would calculate quite an unbalance between the phases. But on a continuity test, it wouldn't show that. They would all show as 10 milliohms. So it looks balanced. When you have the extra resolution of the 4-wire Kelvin measurement, then you can see the actual values and that they are unbalanced. We have our type T temperature probe here, which is standard. So we can plug that into the tester. It will automatically show us the temperature of the winding that we're measuring, where we're touching the probe onto. It will go into the display, and then we can click the save button to capture that temperature. Or we can use the controls on, as we see on the right, where we can actually enter the temperature manually. So we'll measure it with a different system, maybe a handheld infrared gun. We'll then enter the temperature manually. We'll press accept and then save, and that temperature is taken through to the IR test for the correction. The importance of correcting the IR values for temperature is because that the temperature affects the IR values greatly. So the rule of thumb is for every 10 degrees Celsius increase in winding temperature, the IR value halves. So if we don't make a correction for temperature, the trending of the IR is impossible, particularly in countries where you get great fluctuations in temperature, summer to winter. So in the UK, we can have 0 degrees C. In summer, if we're lucky, we might have 30 degrees C, and it can be anything in between. So if we're not correcting to 40 degrees C, which is the IEEE 43 standard for correction, then those IR values will be changing greatly, and it's impossible to trend. So the voltage measurement feature is a little unusual for this type of handheld tester, but it provides a useful suite of tests. Voltage can be measured across 3 phases simultaneously. As you see in the upper left-hand image here, so we've got 414 volts phase to phase, and we're also looking at the phase rotation and also the frequency. Frequency can be displayed up to 400 Hertz. And then we also have our phase rotation test, and that will indicate the power supply's phase rotation, L123 or L321. And that will help us when using the motor rotation direction test later to ensure that when we start the motor, the shaft will turn in the correct direction. We'll have a physical demonstration of that. Why do we care about voltage level? Well, motors are designed to work with plus minus 10% of nominal voltage, but ideally they should be less than plus minus 2%. Voltage unbalance is also crucial, and a 5% voltage unbalance can produce as much as 40% current unbalance. And operating with over voltage or under voltage and or voltage unbalance, then we see the effect in the power supply, the motor performance, the efficiency, but also the temperature within the motor. It will induce higher temperature in the motor, and that will reduce the installation life of the machine. So this really relates to reliability. We need to be sure that our power supply, our power quality being fed into the motor is of the right level and balance to avoid overloading our motor thermally. We also have our dynamic tester, the EXP4000. That's actually designed to test a running motor, and it will look at power quality and apply thresholds automatically, as well as looking at things like rotor bar, percentage load, calculating the torque level, and also the fluctuating of the torque. So the sequence of the phases must be determined to ensure that the motor rotation direction will be correct based on the connection of the winding. This will ensure that the load operates correctly. So, for example, the fan will blow when it should, or suck, depending on what the function is. Applies to pumps and lifts or elevators. So the MTR will display that measured voltage between the phases, and then also that sequence L1 to 2 to 3, confirming that rotation. And then we compare that to the motor rotation direction. And if we have the same L1, 2, 3, then we know that the motor will rotate in the correct direction. So this is how we look at the motor rotation direction. So we've checked the supply rotation first, and we have maybe one L1, L2, L3. We then connect our 3 leads to our motor winding. We turn the shaft in the direction that we want the motors to turn in. And if we also get L1, L2, L3, then we know that the motor will start in that correct direction. And this can be crucial in some motor-driven applications, as the incorrect rotation can cause damage to the driven equipment, such as pumps, compressors, gearboxes. The bump test is a commonly used test, but this will cause damage by using this method on some machines if it goes the wrong way, unless you decouple the motor from the load. And motor direction of rotation is defined by an international standard, IEC 634.8, where the following criteria are established. So the direction of rotation must be established on the coupling side of the motor. The coupling side is where the shaft extension exits from the motor. And for motors that have a shaft extension both sides, then it's generally the end with the largest diameter. And if the 2 shafts both have the same diameter, then it's the opposite end from the fan. We also have the diode test, and many motor systems include semiconductors, and the diode test is included and particularly relevant to the rotating diode pack of alternators. So we can check that the diode is functioning correctly. We have our LCR meter, where we can measure inductance and capacitance, and they are frequency selectable to 120 or 1 kilohertz. We also have an auto mode for the LCR meter, and then the MTR will automatically determine if the load is inductive, capacitive, or resistive. So to test a diode, the MTR measures the voltage across the ends of the diode in both directions. A diode in good condition shows between 0.5 and 0.8 volts in one direction and open circuit in the other direction. If we have a shorted diode, then the tester shows 0 volts in both directions. And if we have an open circuit diode, we get an open circuit reading in both directions. Inductance measurements can be useful for detecting stator winding problems, even when the resistance measurements do not indicate a problem. The resistance measurement of a phase can vary very little with a single shorted turn, because the resistance is linearly proportional to the length of copper wire, whereas the inductance is exponentially proportional to the number of turns. So it is much more sensitive to those changes if we have a short. I saw a case a few years ago with a salient pole generator rotor. I measured the 4 coils separately, and the 4 coils had very similar resistance values. I then measured the coils using the inductance test, and one of the 4 coils had a vastly different value, and it was hence faulty. So resistance doesn't always show you the problem. And with inductance, we can detect such things as inverted coils or reversed connections, reversed phases, eccentricity, short circuits, we've already said. But let's be clear, this is a welded short circuit within a phase or even between phases. It's not detecting weak insulation between the turns. That's where we need the surge test, which is another discussion completely. We can also see rotor porosity and broken bars for example, using inductance. So the goal of each function of the MTR, what are we really looking to find with each test? So the IR suite of tests will check the ground wall insulation, and it can also be used for the phase-to-phase insulation. But again, to check phase-to-phase, you have to be able to open the neutral point of the motor. So we're looking for contamination and things like that as well. The DLRO test, or the Kelvin resistance test, we're looking for the magnitude of the phases, but also the balance between the phases. And this can indicate short circuits, open circuits, and also bad lead terminations or connections. The LCR meter provides us with the inductance and capacitance. And as we said in the previous slide, inductance can help us detect winding faults, such as a reversed phase. And that's something that winding resistance cannot do. And I can show you that later. The capacitance test can be used to find contamination in the winding to earth. But again, this has to be a trending test. We don't necessarily know what is a good or bad value. So we need to really trend that over time. And again, the voltmeter allows us to measure the voltage in the circuit or even between phases, of course. But we also have the true RMS voltage measurement for measuring the output of an inverter drive, a VFD. Plus, we have that all-important rotation direction of the power supply, which will help us ensure that the motor rotates in the correct direction when used with the motor direction test. So the recommended sequence of tests when using the MTR105 on an induction motor is, first of all, to check the resistive unbalance between the phases. And typically we look for an unbalance of less than 3%. And that's calculated by taking the maximum value, less than minimum value, divided by the average, times 100. The vast majority of motors are less than 1% unbalanced, but some motors are actually higher than 3%. A two-pole motor is a good example. That could be as high as 5%. So we need to really consider that when we're testing different types of motor. And again, trending over time is great because we know what we should see based on the last test. We should then check the inductive balance between phases. Again, we're looking for about 3%. However, we have to consider that when the motor is assembled, the rotor can affect the inductance of the phase or phases. So this depends on the design of the rotor and also the air gap. Some rotors have very little influence on the stator inductance. Others have quite a big influence. So if you know there's no influence, then you can use inductance testing with the rotor present. If it causes a big unbalance, then you can only really use the inductance when the rotor has been removed. And again, we're looking for shorted turns or that winding fault, reverse connection, reverse phase. Then we have our IR test and our PI test. This is looking at the ground wall insulation, and again can be used for phase to phase if we can open the neutral point. And this is where we're looking for a certain value of megohms. Ideally, for an IP55 machine, we would recommend greater than 50 megohms at 1 minute and at 40 degrees C. Remember that temperature correction. Or if we have a form wound winding, then we would say greater than 100 megohms at 40 degrees C. And then for IP23 machines, we would recommend greater than 10 megohms at 1 minute, again at 40 degrees C. And we're looking here for contamination, moisture, and even potentially damaged insulation. And then finally, we have the PI test or the DAR test. PI test is typically performed on high voltage machines only. and we're looking for that contamination mainly, but also brittle or damaged insulation in the slot portion. So it's important to look at the standards and to understand what the standards say, certainly in terms of applied voltage. So for the IR test, which also covers the PI test, we can look at the IEEE 43-2013 standard. And this is the recommended practice for testing insulation resistance of electrical machinery. So if we look at our winding rated voltage, so less than 1,000 volts. So now we're talking of 400 volt motors, 690 volt motors. The recommended insulation resistance test voltage is 500 volts DC. If our motor is 3.3 kV, then we'd be in this third row. So the correct voltage for an IR test on a 3.3 kV motor is 1,000 volts or 2,500 volts DC. So these are the standards that you should be following when you're testing your motors. So we know what voltage to apply, but what is a good or bad IR value? Well, depending on the age of the winding and also the type of the winding, the value changes. If we only consider modern motors today, and that's sort of after 1970, then we're looking at these second and third column or row. So we can see that for AC windings built after 1970 but form wound, then the minimum IR value should be 100 megohms, and that's at 40 degrees C. So we have to make that temperature correction. And then for random wound windings below 1 kV, so this would be typically your low voltage motors, then we're looking for 5 megohms or greater at 40 degrees C. So these are the standards. These are the values that the standards recommend as a safe working minimum. But really 5 megohms is quite low for if we're talking about reliability of motors. So we would recommend at least 50 megohms at 40 degrees when we're talking about reliability, or even higher, even the 100 that's suggested for form wound coils. And the important point to remember is that we must measure the winding temperature and then use that to correct to 40 degrees C. We can then trend those values over time, but we can also make sure that at 40 degrees C, we do have a value that's higher than the safe recommended minimum. The PI test is generally performed only on high voltage machines, and it's a 10-minute IR test. We take the 10-minute IR value, we divide it by the 1-minute IR value, and that gives us the PI ratio. Typically, the PI ratio should be greater than 2, but the standards again cover that depending on the type of insulation, and sometimes the location of the motor. If it's a very difficult environment, then customers may accept a lower PI ratio based on their experience. IEEE 43 states that if the IR value at 1 minute is greater than 5 gigohms, then the PI test may not be meaningful. They state the PI is dedicated for high voltage machines, but some customers would also perform a PI test on a large low voltage machine. And then some for those low voltage machines would use a DAR or dielectric absorption test for the low voltage machines instead. What we're looking for with the PI test is for the dipoles in the insulation to polarize as we apply the DC voltage. And we're looking for contamination and moisture could be shown by a low PI ratio. But it's really a trending tool. We wouldn't take the motor out of service because it has a low PI test necessarily. we would trend it, or potentially we would dry the machine and retest it to see if it's a moisture problem. So one question that comes up occasionally, maybe in the middle of a PI test, this test has to stop for some reason, and then I've seen customers repeat the test immediately. Is that a good thing to do? And the answer is no. If you've run a PI test for, say, 6 minutes and then had to stop the test for some reason, then there will be a residual charge within the installation. And that means that when we run the PI test again, we will get skewed readings. So before retesting, you need to completely discharge the windings. And the standards say that you should discharge for at least 4 times the duration that you applied a DC voltage for previously. So if you've done 6 minutes on a PI test, you should discharge for at least 24 minutes before you rerun the test. So the MTR can save a full suite of tests for up to 256 motors. We can assign a folder in the MTR in the settings screen. It could be the job number, or it could be the asset number of the motor to be tested. All tests get sent into that folder, and you can then transfer that data at the end of the testing to a USB stick, take it to your PC, and import the data into the PowerDB Lite software. And then from there, you can generate a professional report. So again, this is one of the other benefits. If you have 5 or 6 separate single function testers, if they're all from Megger, then potentially you can put them into the same report. But if you've got different manufacturers' brands, then it's very difficult, because you won't be able to create one nice report within the same software package, or you'll have a much more difficult way to do it, maybe generating into Word, copy and pasting data to try and make a professional looking report. So this is a real benefit. Let's have a look at a typical test report. So you can change your logo. You can import a logo and replace Megger. You have your nameplate data, so you can maybe have a customer name, location of the equipment, that sort of thing. And then we get down to our test results. So we have our winding resistance tests, 46.8, 46.9, and 49.3 ohms. We have our direction of rotation, L123. We have our IR tests. So we did the temperature compensated test at 500 volts. We had 28 gig ohms at 25.5 degrees, and we had only 14 gig ohms at 40 degrees. So that is the corrected value. We did a 3-phase test. So U to V, 30 gig ohms, V to W, 30 gig ohms, W to U, 30 gig ohms. And we did a DAR test, and we had a ratio of 1.07. We measured the inductance phase to phase. We had 124 millihenries, 121, and 126 millihenries. So we had a slight unbalance, but again, depends if the rotor was present or whether it's a non-symmetrical winding, such as a 2-pole. And we measured capacitance at 1000 hertz, 1 kilohertz, and we had 700 picofarads. So if we'd measured voltage, any of the tests that the MTR can perform, if we'd performed those tests and saved them, then we can import that data into this report. Okay. So I'm often asked what's the difference between the Baker testers, the Megger Baker testers, and the MTR. So a Baker tester, for those that haven't heard of them before, it's a high voltage multifunction tester specifically designed for testing motors and rotating machinery. It provides IR, PR, PI, DAR, DC step voltage, DC high pot, and also the surge test. And that's used for detecting turn-to-turn and face-to-face insulation weakness. The testers can also offer winding resistance using the 4-wire measurement system, and also inductance and capacitance in some units. But the MTR is a low voltage test. And what does that mean for us? It means that because it's low voltage, it's not able to find weak insulation. So when you're talking about motor reliability, to be sure that the motor will be reliable from the winding point of view, you need to be able to apply high voltage to find any developing weaknesses. So the MTR won't be able to do that, but it still has huge value, and it's extremely complementary to the Baker testers. The Baker DX and AWA testers can highlight weak insulation between the winding and earth or frame, and also between turns using the surge test. Tests are performed at twice the rated voltage of the motor plus 1000 volts, so typically 2 kV for a 400 volt motor. Baker testers are needed for when we're testing reliability, when we have critical motors that have to keep running. The MTR can't give you all of the answers for a critical motor because we're not using those higher voltage levels. So there could be a reasonable number of megohms at 1000 volts, which is the maximum voltage of the MTR, but at 1500 volts, winding to frame, there is a damaged area. The MTR won't find that, but the Baker testers will. So these are some of the differences between the units. But it's important to say that many existing Baker customers, Baker users, they also use the MTR because it provides some very useful tests. It's a low-cost handheld unit, very portable, and as I say, it really complements the Baker testers. Most customers only have 1 or 2 Baker testers, but often numerous MTRs. Because of that, investment is much more easily approved, and therefore very often service engineers will have an MTR in the van, in every van that goes out to site. So who should use an MTR unit? Well, really anyone who's involved with motors, whether that's motor repair companies, motor and generator manufacturers, pump manufacturers or repairers, and service companies. So they are companies that don't do motor repair, but they do motor testing. And then we come on to industrial companies, really any industrial companies, because industry is driven by electric motors. Anything that rotates is generally driven by a motor. So paper, steel, water treatment works, petrochemicals, power generation, marine, food and beverage. As I say, anyone who is using an electric motor, they should be testing on an annual basis. And the MTR is a fantastic tool for this. So what's included in the MTR? So the MTR comes with its own carry pouch. We have the MTR itself, of course, and then we have the 4-wire Kelvin clip lead set. On the right here, we have our high voltage lead set on the left here with the plug-in grabber type leads. Sorry. We also have the long reach type probes, which can be used particularly for voltage measurement. And we have our type T thermocouple. So that is all standard. The standard unit is powered by AA batteries, and we have an optional recharging kit which comes with rechargeable batteries. The other option we have is instead of the 4-wire Kelvin clip lead set, we can also have a duplex probe kit. So that is for measuring bar-to-bar winding resistance on DC armatures, for example, where you have your two probes on each bar measuring the resistance across. Okay, our next webinar is planned for covering the high voltage Baker AWA multifunction motor analyzer, which we spoke about briefly a few slides ago. It's widely used by motor rewinders, manufacturers and industrial companies. And that webinar will help you to learn how a mixture of both low voltage and high voltage testing can help you understand the condition of your critical motors and therefore the likely reliability of that asset. So invitations will follow in due course. We're going to run a live demonstration now, and then we'll come back for a question and answer session. So here we have our standard kit. We have our MTR, we have our soft case, carry case, we have our recharging kit, which is optional. We have our high voltage test leads, we have our long reach test probes, and then we have our grabber type clips for generally for IR testing and inductance testing and so on. And then we have our type T thermocouple for measuring winding temperature. Okay, so what I want to do now is go through a demonstration. I'll just move across to my motors. Okay, so actually, first of all, what I'm going to do is, before we run a test, we want to turn on our tester. We'll just let it boot up. And we're going to go to our settings. Sorry, our folder icon here. And we can then scroll through various jobs or folder names. I'm going to choose demo. And it says at the top, press save to assign. So when you press save, then you've selected that folder to save all your data in. So the first test we're going to do is winding resistance, low ohms measurement. So for this, we're going to use our Kelvin measurement leads. Now, if we're not sure how to connect them, we can press the lock button and the screen now gives you an example of how to connect the test leads. So each clip has two connections. So we want to connect red, black, black, red. Okay. So that's our connections. We can press the lock to go back. And now we're going to measure the winding resistance across our three-phase winding. Okay, so we're across phase U and V. We press the test button. And we've got 46.5 ohms. We can now go across V and W. We've got 48.4 ohms, and we can go across W and U. And we've got 51.2 ohms. So it's a little bit higher than this morning, mainly because the temperature is increasing. So if we calculate the unbalance between those three phases, we take the maximum value less the minimum divided by the average times 100%. That gives us an unbalance of just over 5%. And that's because these stators are two-pole, and two-pole windings are not symmetrical. So we have an unbalanced winding or resistance. But that's a brand new motor. That's a good winding. We can also test our second motor. .3. .4. It's not so easy with a very small terminal block. And then W to U. 46.4. So very similar values because the windings are the same design. And this is a This is a 400 volt, 50 hertz, 0.3 kilowatt motor, and two-pole. Speed is 2,780 RPM. Okay, so that's resistance. What we can do now is change to continuity. Now, obviously, if we wanted to save the data, we would run a test. We would press save, and it tells you here you've saved it to demo, and it's got a time and date stamp. Okay. So now what I want to do maybe is go to inductance. So we go to our LCR test. And again, we need to change the leads. So how do we connect the leads? If you're not sure, press the lock button, and it tells you just use the red and black leads. Okay, so red and black. Red and black. And now we're going to connect across our winding. So I'm going to connect across phase U and V. Okay, this is a standard motor connection. So if I can just show, hopefully this will focus. So with a star connection, which is the top connection, we have got L1, L2, L3, which is we're going to connect to those phases. And the star connection is made up of U2, V2, W2. So we've got phase U with the two ends U1, U2, phase V with the ends V1, V2, phase W, W1, W2. To make the star point, the manufacturer uses U2, V2, and W2 connected together with the links, which is what we can see here. So that's what we've got in this motor. Now in this other motor, I've actually made a reverse connection. So instead of having blue, brown, black, I've actually got brown, pink, black. So I've swapped over blue and pink. So pink is V2 and blue is L1. So now we've got, instead of all the two leads making up the star point, we've got a one lead mixed in with the other twos. And that's what we call a reversed phase. Okay, so if we now measure inductance of the two stators, we can see what difference that makes to our readings. So first of all, we're going to measure the inductance of the good stator, which is this one. So inductance, we've got 113 millihenries, 115 V to W, and 119 W to U. So slightly unbalanced, but again, that's because it's a two-pole winding. So now I'm going to test my other stator. I'm going to go across what effectively we think is L1 and L2. And I've got 70 millihenries compared to 114 or so. I go across WU. I've also got 70.7. And then I go across WU and I've got 114. So you can see that the two phases, which I've swapped over, blue and pink, gave us those different values of 70 millihenries, where it should be around 114, 115. So clearly, inductance can tell us when we have a winding connection issue. But let's go to continuity now. What does continuity show us? So if I go across the good motor, we've got 46.1 ohms, 46.0, and 48.5 ohms. Now let's compare that to the other stator, U to V. Yeah, 46.1. V to W, 48.6. W to U, 46.3. So the two windings, from a resistance point of view, are the same or very similar. That reversed phase hasn't affected resistance because the amount of copper in the circuit hasn't changed, it's identical. But inductance is affected by coil shape and many other reasons, and inductance is able to pick up that reverse connection problem. So if you're just testing using winding resistance and IR testing on your motors, if you're a motor repair company, you can very easily send out a motor with a reversed phase. Okay, so what we want to do now is a IR test. So we can use the same motor. So we put one live lead onto the winding, which is star connected. We'll put the ground lead onto the earth point. There you go. And what we want to do first is we actually want to measure temperature, don't we? So if we go round to the temperature setting and we'll plug in the temperature probe. If we're not sure how to do it, it tells us how to do it. We're going to measure now the winding temperature using the probe. And yeah, I would say it's at 25 degrees. I'm pretty hot in here. I've got the sun coming in through the windows. So 25.4 degrees. I can save that. That's now saved. And I can now go to my IR test, and I want a 500 volt test. And it's telling me here I've got IR. I've also got the 3-phase option, PI, time test, DAR or dielectric absorption, back to IR. And I can now switch on my temperature correction mode. So now if I run a test, I need to connect my leads again, otherwise I have no reading. The joys of doing a live demo. Okay, so press and hold the test button. I can lock the button if I want to and leave it running. So we've got 35 gig ohms. If I then stop the test, so we had 35 gig ohms at 25 degrees. Tester has corrected the IR value to 40 degrees, and we have 18 gig ohms. So this is the kind of difference that temperature makes to our readings. I need to save that information to our demo folder. Okay, and then the last test I want to show you is the motor rotation direction test. So this is a 3-phase test. We need to connect all 3 phases. So again, if you're not sure, press the lock button and it tells you how to connect the leads. I need to add my blue into the top. So we've now got red, black, blue. And I'm going to add so the sequence is red L1, black L2, blue L3. And actually I want to change, I do want to change that that motor. So let's get rid of these 2 and bring in my assembled motor. Obviously we need the rotor fitted to be able to run this test. So red to L1, black to L2, blue to L3. Okay. Press lock. So we have our direction of rotation. It's not displaying anything yet because we need to rotate the shaft. So let's say we want the motor to turn in the clockwise direction. If I turn it clockwise, then you see the displays L1, L2, L3. If I turn it in the anti-clockwise direction, it will reverse L3, L2, L1. Clockwise, L1, L2, L3. Of course, to change direction, you just reverse 2 phases on your power supply or on your motor connection. If I now turn clockwise, I should get L3, L2, L1. Okay, so it's pretty simple. We just need to check our power supply rotation And if we've got on the power supply L1, L2, L3, we then come to the motor, we connect our leads, red, black, blue, we turn the shaft in the direction we want. And if we get the same L1, L2, L3, we know that when we connect that power supply into the motor and press the button, the motor is going to turn in the clockwise direction. Okay, that's about it for the demonstration. I can't demonstrate the power supply direction, rotation, but I can obviously show you the screen. So this is our voltmeter. We have our soft keys here, so I can scroll through the tests. We've got AC measurement, we've got DC measurement, we've got supply phase rotation. So this is where it would measure phase to phase, L1 to 2, 2 to 3, 3 to 1. And it would then give us the direction of rotation. It will give us the frequency, and the direction of rotation would be L123 or L321. If we go to continuity, didn't turn it quick enough, so it's just rebooting. So within continuity, we've got diode check, bidirectional, unidirectional. Okay. And then some of the other things in settings, we can change our timings of our DAR test, for example. We can look at the threshold, insulation threshold. So when we do an IR test, if the IR value is below a certain level, we'll get an indication. Temperature correction. How long is the timed insulation test? And for the variable voltage setting, which is, if I go to here, this setting here, I can actually set a specific voltage to test at. Any voltage between 10 and 1000 volts for the IR test, but I can only change by 10 volt increments. Language, backlight, type of batteries, and so on. Okay, so that is the MTR105, a fairly short demonstration. Hopefully you saw the ease of use, the screen, the display. It really helps you to understand how to check your leads, how to run a test. It's very logical and easy to use. But obviously Megger and our distributors are here to help if people have any questions. Okay, so thank you for joining the demonstration, the live demonstration, and we'll now go back to the webinar for our live question and answer session. Okay, thank you.